right, here we go. Physics reaction video number 21. Looks like we're doing some equivalent resistance stuff. I'm just going to move me out of the way, I guess. There we go. Actually, I'm not sure why it's not going full screen, but maybe I hit F11. There, okay. So we'll move me over here. And anyways, here we go.
All right, in this lesson, we're going to look at the difference between series and parallel circuits.
Excellent.
And then we're going to learn to calculate what's called the equivalent resistance. Let's talk about that first. Equivalent resistance is another way of saying the total resistance. So I'm going to write down RT.
Okay.
In a circuit, we usually have more than one resistor. When you have more than one resistor, then you have to calculate the total resistance of the circuit. And it's a little bit more complicated than just adding up the resistors. And the other thing I want to mention is that
I think it's so interesting to think about total resistance, and really it's asking how much the battery has to deal with, right? You have to be careful with your words there. You can't say how much the battery has to work or push or power or energize. You have to be careful with your words, but deal with works for me, right? So how much resistance does the battery feel like it's getting hooked up to? Because it doesn't know, right? It just feels something. And so I like that idea of total resistance instead of equivalent resistance, because equivalent makes it seem like it's almost fake. Like we're going to do this fake other circuit, which we kind of are, but it really is the total resistance of whatever's being hooked up to that. So sometimes you'll do, hey, what is the equivalent resistance of just say these two? Well, okay, so you'll get, some answer, and that you'll say, well, that's not what's being hooked up to the battery, but that's what's being hooked up to this point here, right? And maybe you could think of this as some weirdo battery with a parallel internal resistance. That's weird. So I really like how she's talking about the total resistance.
Is that this skill of learning to calculate the equivalent resistance is the first thing that we need to be able to do as we move into our next lesson. And you will not be able to do the next lesson unless you know how to calculate equivalent resistance. So please take your time on this and make sure that you really, really understand it.
Yep. We're developing muscles.
Number one.
To do cool stuff later.
A circuit is a circuit in which the current passes through each circuit component without branching. So the current passes through each circuit component without branching. All right, what I mean by that, it's going to be
that's cool,
convenient for you to always picture yourself being a marching electron. So right now, if you are a marching electron, you are going to come out of the positive side of the battery. Remember conventional current. Okay, so here you go. So we're going to picture you and
So I do this thing in class where I say, okay, repeat after me, get ready. We're gonna chant something, and they get all ready. I say, damn you, Ben Franklin! Because what she said, right, is not right. That's not the direction the electrons go. The electrons actually go the other way. And of course, the other problem is they don't make it actually that far, right? So the drift velocity of electrons is really slow. So no single electron actually might even make it all the way through the current. And then when you get to AC, they definitely don't. They basically stay in the same region they're at when they start. So I love this, though, this anthropomorphism. Like, I want you to imagine your electron. I'm just complaining about Ben Franklin here. But did you hear it? So first of all, she paused. I don't know if you caught it, but she hitched when she said the positive terminal, because I'll bet you anything she was thinking, damn you, Ben Franklin. And I'm sure that's apocryphal, by the way, but it's fun. We claim that Ben Franklin made the choice of which way the current's flowing, and then it happened to be not where the moving charges were. And right, it's hard to have known back then. But anyways, she said so that she had that hitch, and so I'm guessing she thought about that, and then she used this phrase, this conventional current phrase, before she drew that arrow. And yeah, okay, fine. So we're dealing with situations where positive charges are moving, I guess, clockwise through this current.
And I draw the marching ants or the marching electrons with dots. So here go the dots. Marching electrons go around. They go through resistor 1. They go through resistor 2, march, march,
Cool.
march. They go through
March,
resistor
march, march.
3, and then they're back at the battery. That
And the way she did that is super cool, right? Because it is, in fact, a gigantic train of electrons. And so that's why sort of they have to move together. If you think about it like a train on tracks, they can't squish each other.
That's what we mean by without branching. We made a complete circle. If you make a complete circle, you have a series circuit.
Cool.
All right, but look at a parallel circuit. Is a circuit in which the current divides into 2 or more paths. So I'm going to write down the word current has a choice. Current has
Ooh.
a choice.
That's cool.
All right, so here you are. You are the marching electron coming out of the positive side of the battery. So march, 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 right there. I'm going to circle that little dot. That dot is called the junction. A junction is when you have a choice. You now could go through R1, so you could go like this, march, 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 march. And you could be back, or maybe your friend came out of the battery and went like this.
Oh, different color.
March, march,
Interesting.
march, march, march. Oh,
Interesting.
look, he has a choice. He's reached a junction.
So that second color helps her, well, although it's kind of hard to see. Oh, no, I can see it pretty well. Is helping her make her point. But it's not like they've pre-selected, right? So the electrons coming out of the battery haven't pre-selected which way they're going to go. So this is tough, right? And that's why, again, I love video as a medium. She's really saying things super, super well. She's adding some color, etc., to really drive home her points. But you could imagine that if all you did was write all this stuff down and then handed the sheet to your students, they'd be like, okay, well, apparently there's some red things and there's some blue things. I'm not really sure what's going on. But the video allows her to really explain that. So this is really cool. And I love also the scaffolding that she's doing here, right? So these are the two major things, series and parallel. And she's really taking her time before doing it. So yeah, I think that's cool.
Junction. He could go instead through R2, march, march, march. Or you have another friend who went march, 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 march. He went straight. And so you see we have 3 different paths.
So this is really, really great. And I'm starting to think about the types of things that my students struggle with when I teach this. So you've got the student who wonders about the electron that might go like this and then up here, right? And so you have to say, well, no, there's this direction of flow that they can't really sort of flow back upriver. And so it's interesting that I often will use plumbing or water-based analogies, but it's so fascinating that some people don't have a lot of experience with plumbing. In fact, in my own home, when I have plumbing problems, I usually have to convert it to a electrical problem. And then I'm like, oh, that's what's happening. And then go back to doing plumbing. So some of the analogies we use, I think, are obviously work for some and not for others. And she really hasn't used many analogies yet. Basically, she's talking about, I heard her say ants and obviously electrons marching. So we'll keep an eye out for that.
We have this first path right there. We have a second choice. And
lots of representations here. I love it.
3 ways to get around this circuit. So it doesn't matter how many choices that you have or how many ways there are to get around.
It's interesting. Also, people will encourage students to do these Kirchhoff laws things, which my guess is she's a couple of lectures away from. And you could do a Kirchhoff's law like this. You could go, right? I mean, you can do whatever you want as long as you start and end at the same place. And so if you read my blog post, maybe I'll put it in the description below. I struggle with Kirchhoff's laws because of those sort of arbitrary directions you're able to loop around a circuit. So obviously I put a lot of time and effort into thinking about ways to teach this stuff, but this very, very early stuff is super, super important. You have to drive this stuff home before they can start to tackle some of the more complicated circuits.
To get around the circuit, anytime there is a junction, that there's a choice, you have a parallel circuit. So that's just the only part that you need to recognize. But in real life, our circuits, if we had them built on our table, it's not as always easy to see. So let's pretend this is our lab table. We have a battery here. We have a wire connected to the start of a switch. Then they have a switch. and another wire, a light bulb, wire, light bulb. Okay, so now I have to draw this circuit. And when you draw a circuit diagram, you have to make it boxy. And I
Ooh.
try to make it as close to the replica as possible. So I see the battery over here. So I might do something like this. I'm going to make the positive side of the battery here just because I feel like it.
Not just because she feels like it. She's got a plan. And so that pause, right, was like, I guess I said I'd come out this way. And I can't quite see that battery. I think this is a Duracell coloring, and I think this is actually the positive side of the battery. But she, I think, wants to have the switch be early. So this, eventually they learned that it doesn't matter where the switch is. But my guess is she wanted to put the positive of the battery down low so that the switch was the first thing that her sort of mythical marching electrons run into. But right away, you might have a student like, what? Huh? I thought batteries were drawn this way. And so I love the notion that she could just draw it either way. And the other thing, of course, is these type of light bulbs are going to light up either way you could put this battery, which is super cool, right? Not everything works that way, but super easy incandescent light bulbs work that way. And unfortunately, sometimes in a physics lab, it's the only place they ever run into light bulbs like that. But no, I thought that was really, really cool how she thought carefully about this battery. Also notice that she's not really worried too much about the original lines that she drew. Batteries usually don't have a line through there. And I'm guessing she's going to draw a couple of resistors up here, which you also usually don't have the line through it. But I like this box scaffolding that she's doing. Obviously, you don't have to, but she really wants them to sort of have everything organized. And since wires are flexible, we can do it.
And that would mean my electrons would be going this way. And then I'm going to put my switch in. A switch is like a door. So I just put a door. And so the door can open and close. And then I come around and I see a light bulb. A light bulb is a resistor. And I see another light bulb over here.
Cool.
Now, because this is a complete circle, I honestly could have put these components anywhere I wanted them on the circle. It would not have changed my circuit in any way, but I try to make my diagram look as closely
That's cool.
As possible to mimic the.
And I'm contemplating when I'm walking around lab when students are working on this stuff and I'm looking at their circuit diagrams, I'm always like pointing to things on their diagrams. So I'll point to this and I'll say, okay, where's this? And they'll say, in real life, that's here. And they'll say, oh, where's this? And it's there. And it actually is super helpful if they're drawing it like this. And there's no problem with this, right? If you train your students to do things a certain way, you're going to be faster when you're walking around lab helping them or walking around in the classroom. So if you were to say to students right now, like, hey, you guys can draw this any way you want, order doesn't matter, I don't care if it's a rectangle or not, technically a true statement, probably they'll get the right answer at the bottom of the page. But if you're walking around, you want to be able to rapidly look at their pages, say, whoop, 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 hey, wait, what are you up to? Hang on a second. And so if you are the one indoctrinating these students into how to tackle these problems, why not make your life easier so that they're all building it quite similarly so that you can go around and help them faster? Now, you've heard me complain about indoctrination before, where it's like, oh, shoot, what happens when they go to another physics class and somebody doesn't have them do that? Well, this particular indoctrination is not going to have them get the problem wrong, and it's going to have them be able to get more help from you when you're stopping by. So really, it's just a matter of pulling the scaffolding away later. And so this is great scaffolding you're building. So contemplate, what does it look like to pull the scaffolding away when they're really doing cool things later on?
The actual circuit on my team.
All right, so I'm just going to stop right there. Some very, very cool stuff, some very early beginning work with circuits. Loved it. I loved the colors, the analogies, recognizing the problems to come with Ben Franklin and the stupid direction of current. The indoctrination was really, really cool. So lots of really neat stuff. I've put a ton of thought into how to teach Kirchhoff's laws, which is maybe 2 or 3 lessons beyond this. So I'll put those links down below in the description. So that's it, everybody. Have a great day. 21 of these you can spend every day for 3 weeks watching these. I hope you enjoy them. And remember, physics teachers are awesome.